Okay. To thinking about the structure of the cell membrane, to thinking about how molecules can enter and exit the membrane. So thinking about size, charge, and what parts of the membrane are going to let them through, what process is going to let them in. Again, keeping in mind the reason that cells need to let things in and out is because they need to do things with those molecules. And the things that they are doing with those molecules are metabolizing them. So chapter 8, we are going to be doing an introduction to metabolism. So I think the syllabus told you to read all of chapter 8. We're not going into the level of detail that all of chapter 8 goes into. So the homework is trying to focus you a little bit more on the parts that we are going to focus on. It's a little bit of chemistry, a little bit of physics, and a little bit of biology all in one chapter. So all the fun things together. And remember, biology is the pinnacle of science. We can't learn biology without learning chemistry and physics. You can do physics without any biology, but we need it all because we are just at the top of the pyramid. We're at the big top of the food chain. I don't know. So what do we mean when we say metabolism? So cells are bringing in molecules, they're passing molecules out. All of these molecules are involved at some point in chemical reactions. So when we talk about metabolism, we're talking about, sorry, I don't like red. I know I work at a college where the color is red, but we're talking about the sum of all the chemical reactions in an organism. That's what we mean as the biological definition of metabolism. It's the sum of all the chemical reactions that are occurring in an organism. You've probably met someone at some point in your life who will say something like, oh, I have a really high metabolism, or I have a really low metabolism. So, and there's biological evidence that that can happen too, but that would mean more chemical reactions versus less chemical reactions. All of these reactions are some kind of energy transformations. And again, we've kind of alluded to some of these, and we will continue alluding to these energy transfers, the way that energy is moving from one form to another happens in these chemical reactions. You can also think of this as a way of managing the way that an organism is managing the matter and energy flow through its body. So your book gives you an example, I think, of the first page of the chapter. It talks about click beetles, and click beetles use bioluminescence. And here's two more examples of bioluminescence. Fireflies. This is the question I should have asked today. Lightning bugs or fireflies? I don't know what you call them. Some people feel very strongly about this. Some people have never seen one. So all of these are examples of bioluminescence. And bioluminescence is a metabolic reaction where organisms take organic molecules and they convert them to light energy. For a reason, not just for fun, not just because it's cool. In the book example in the introduction, it talks about click beetles, and click beetles eat termites. So they produce this bioluminescence, and that light will attract termites to come to them, and then they eat them. Fireflies, lightning bugs are producing light to attract mates. Organic. If we were in a classroom that had a whiteboard, for the record, I could write better on the whiteboard. I write better big, with small, and fine motor control, not my thing. The left-hand picture is showing you algae that perform bioluminescence, and as I'm saying this, I'm telling you they all do it for a reason, and I right now can't think of the reason that algae do bioluminescence, but they do. And it does look cool. If you go into the water at night and you move your hands, they will bioluminesce. And it's cool. And I will get back to on why we do it. There's a reason. But it's also cool. And I don't think it's just because it's cool. So that is just an example of a kind of reaction that is part of the metabolic reactions. So when we talk about metabolism, this is concept 8.1. I'm trying to maybe give you some guidance on where this is coming from in the book. So this is concept 8.1, is talking about metabolic pathways. So chemical reactions are often a multi-step process with the goal of starting with one thing and ending with something else. So in this case, we've got the starting product, not the starting product, that's a terrible way to say that. The starting molecule, A, and we're trying to get to this product, which is D. Sometimes it's as simple as A turns to B, but sometimes it's a multi-step reaction. So I think your book talks about metabolic pathways like a map. So if we want to turn A to B, every step, and from here on out, we're going to just talk about these all the time. Every step is going to involve, and that's not going to show up very well, is it? Nope. An enzyme. So we might have molecule A, it's acted on by an enzyme that produces B. B is what we call an intermediate product. And now this won't show up. And then B is acted on by another. Okay, you know, the Sunday school answer to every question is Jesus. In biology, when we're talking about reactions, the answer is enzyme, always. Why is this happening? It's an enzyme. There must be an enzyme involved in some way. Okay, B is acted on by an enzyme to produce an intermediate, again, which is C. Still not where we're trying to get. So we're going to need another what? Enzyme, yes. And that enzyme will allow us to change our second intermediate into our final product. This is a very generic example, so I'm going to show you a more specific example. Okay, we'll go back to that slide more. This is showing you a metabolic pathway that produces the pigments that are giving fruit fly eyes their color. In week 10 of lab, you're going to do a lab and you're going to look at this metabolic pathway. And I thought, wow, I can show it to you now. And you can see it again later. You're going to take little fruit flies and you're going to smush their heads and you're going to crush their heads and you're going to do chromatography to look for the pigments. Okay, so this is showing you what a metabolic pathway looks like in real life. This is our best understanding of it. We don't necessarily have a perfect understanding of it. But what does this structure look like? What does this look like here? Does it look like anything we've talked about recently? Like a cell membrane? So we've got a phospholipid bilayer, and we've got some proteins here that are embedded in the membrane. So these molecules that you see here, GTP and tryptophan, these are starting molecules. So we have starting molecules, they pass through the membrane, and they're acted on all these green squares, and we're not even showing all of them. All of those are enzymes. So when we're talking about an enzyme, in general, the ending that you will see is ACE. So anything with ACE on the end tells you it's an enzyme. OS is a carbohydrate. ACE is an enzyme. So we'll just look at the bottom one. This is called the omicron pathway. So we're starting with tryptophan. Anyone know what tryptophan is? What kind of molecule? It's an amino acid. It's the amino acid that allegedly makes you tired in turkey after Thanksgiving. It has nothing to do with the fact you ate a whole giant meal and all your body is diverting its energy to digesting it, but tryptophan is the one they always blame on making you tired. So we start with tryptophan. Tryptophan is acted on by this enzyme. This enzyme is tryptophan oxygenase. Again, that ACE ending tells us it's an enzyme that produces this intermediate product, which is, I can't say it, but kynurenine. I don't know how to say it. Okay. Then that's acted on by kynurenine hydroxylase. ACE tells us it's an enzyme. And the final product for that one is xanthomatin. You will not need to know how to pronounce these or spell these ever. In Gen Bio, at least. If you become a fruit fly biologist, maybe you will. But this is a metabolic pathway. We've got intermediates, and we've got a final product, and we've got the enzymes that are acting on it. There's another one up here, same idea. We're starting with the starting molecule. Each arrow represents an enzyme, but we're only going to talk about this one when you do it in lab. But you can see it can split even. So this intermediate is processed into two different further intermediates, which then end up as this final product, and this final product. So this one starting molecule ends up with 3 different final products, and 1, 2, 3, 4, 5, 6, 7, 8 different enzymes act on it. Okay, so we're showing you a really simple example. This is actually a pretty simple example too, but I wanted you to see what it might look like in real life. So these reactions, again, every step is catalyzed by an enzyme. And there's 2 different kinds of reactions that are involved in metabolism. There are reactions that are catabolic, and there are reactions that are anabolic. I don't know how you feel about cats. This cat is a feral cat that lives in our neighborhood, and she's been in our yard all summer, and we've watched her rip the heads off chipmunks 2 in 10 minutes and leave just the tail. So we nicknamed her Vicious. And on Monday, she brought her 4 little kittens into our garage where there's a fish tank. So now I have a cat with in a fish tank with 4 little kittens. And she does not like us. She hates us. Are we feeding her? Yes. Are we providing shelter for her? Yes, and she hates us. So if you get any closer, like if I'm from here, then she goes. So I'm using her as an example of a catabolic reaction. She would like to tear me apart. Okay, does she want to eat my food? Yes, but she doesn't want me to get anywhere near her. Catabolic reactions are reactions that, like a cat, can break things down. That's how I've always remembered it, but this cat is making it, just cementing it. For the record, I like cats. I had a pet cat. We're trying to steal her kittens, so maybe that's why she doesn't like us. I don't know. But catabolic reactions, I just think of the claws of a cat tearing something apart. An example of a catabolic reaction is cellular respiration, which is our next chapter. It takes organic molecules like sugars and breaks them down into carbon dioxide and water, giving us the products that we want, which is energy. These are also what we would call downhill reactions. In terms of energy, they're going to happen more spontaneously. You can think of them like a ball at the top of the hill is going to roll down. You don't have to help it. Okay, the opposite of that is anabolic. So we have catabolic pathways and we have anabolic pathways. What do you think anabolic pathways do? Yeah, so instead of breaking things down, they are going to synthesize or make larger molecules. Oops, sorry. So this is uphill in terms of energy. It takes energy to do this. You can't just make it happen. You have to make an investment of energy. So this is where I hope that you know someone really nice named Anna who's very encouraging to build. So you can remember that's anabolic, or steroids. Anabolic steroids help you build muscle. I'm not encouraging their use, but anabolic steroids do this. So what's the classic example of this? The opposite of cellular respiration. Cellular respiration breaks down carbohydrates. What reaction makes carbohydrates? Photosynthesis, yeah. Oh, sorry. Another example is just protein synthesis, which again, we'll talk about later in the semester in more detail, but taking amino acids and putting them together would be anabolic. We're making something more complex, a more complex organic molecule. So this is where our physics is coming in here. This is coming from 8.2. We're talking about energy being downhill, being uphill, investing energy, that kind of thing. We have to talk a little bit about the kinds of energy. There's two categories. There's potential energy and there's kinetic energy. So what do we mean by, or give me an example of, let's start with kinetic energy because we tend to be more familiar with kinetic energy. Can someone give me an example of a kind of energy that is kinetic energy? What? Wind? So anything that's involving movement. So wind can provide kinetic energy because it's moving air. Heat because molecules are moving around, and the hotter something gets, the more the molecules are moving around, so there's more kinetic energy, there's more heat. There's one more important one. Light, yeah, light is an example. Oh, sorry. Light is an example of kinetic energy. So all of those are forms of kinetic energy. How about potential energy? Some of you in this room have a lot more potential energy than I do. Why? Actually, everybody in this room has more potential energy than I do right now. Energy of location or position. Higher things have more potential energy. All of you are higher than me right now. So you all have more potential energy. So it's energy that comes from position or location. I think the classic example that we give with this is position, but also thinking about like water behind a dam. It's building up, building up, building up, building up. That potential energy it has a lot of potential energy. Sometimes we harness that potential energy by changing its kinetic energy to make electricity. Another really important example of potential energy for biology and chemistry is the idea of chemical energy, potential energy being stored in chemical bonds. So when we talk about photosynthesis and taking carbon dioxide and hydrogen and making new bonds to make it carbohydrates, you're storing energy in those bonds, and then later it can be broken down to release that energy to be useful energy. So it's like stored energy. It's a way to store energy for later. So in this picture over here, we've got a bunch of different people. Which person has the most potential energy in this picture of people diving? Who would have the most potential energy? Yeah, this guy or girl, I don't know, this person has the highest position, so would have the highest potential energy. Who has the lowest potential energy? Yeah, the people in the water. These people have the lowest potential energy because they're in the lowest position. Two people are involved in energy transformations. What has this person done? What energy transformation is going on with the person who is diving? Has taken potential energy because they were up here at some point and has changed it to kinetic energy because now they're moving. How about this person? What energy transformation is going on there? If you're climbing up, you're moving, right? So you have kinetic energy and you're going higher. So you're giving yourself more potential energy. So this is a using kinetic energy to increase potential energy, kind of energy transformation. And that's essentially when we talk about biochemistry, that's what we're talking about. The conversion of energy from kinetic to potential, from potential to kinetic. And all our chemical equations are involved in energy transformations of kinetic to potential or potential to kinetic both. And here's some more physics for us. Okay, when we think about energy transformations and energy changing forms, we talk about the laws of thermodynamics. And there are two laws of thermodynamics. I don't want to limit, there may be more than two laws of thermodynamics, but there are only two laws of thermodynamics that we care about as biologists. If you take physics, you may care more about other things later. The first law of thermodynamics. Anyone know it? Energy can be created or destroyed. Energy cannot be created and energy cannot be destroyed. So that means that the amount of energy in the universe is the same. So we cannot create or destroy energy. But what can we do to it? We can't make it, we can't destroy it, but we can. Right? Yeah, we can change it. We can change it into something else, or we can move it around, but we can't change it. We can't get rid of it. So we can convert it from one form to another, but we can't lose it or make it. It's similar to the law of conservation of matter, which says matter cannot be created or destroyed. So the same amount of matter and energy exists that existed when the world came to be. We just keep changing forms. So we see an example of this here. We've got a bear, caught a fish. So from that fish, it's going to harvest energy. So it's taking the chemical energy of the fish, which is a form of potential energy, and transferring it into kinetic energy to frolic in the water adorably while trying to catch more fish.
So the bear itself here is acting as an energy transformer. So organisms, not just bears. We are just like vessels for energy transformation to happen. That's why we exist, to transform energy. Second law of thermodynamics. We're gonna end today on a terrible note with the second law of thermodynamics. I don't really like the second law of thermodynamics.
It is every energy transfer or transformation increases the entropy or randomness of the universe.
Yeah, it's falling apart. We're falling apart. So every time we transfer energy, it becomes less organized and less useful. So every energy transformation, even though we're not losing energy, we're losing useful energy. So the world is heading towards entropy. And again, I'm using the term lost here. It's not that it's gone, it's just not as useful as it was before. And again, we call this process entropy. Oh, that's not a G, that's a P. So these transformations make the energy less organized and less useful. And we tend towards entropy. When we say this, this is referring to when this energy is transferred, we're talking about spontaneous reactions. There are some reactions that are not spontaneous that help to restore organization to a point. Like classic example of taking things and making them more complex. Photosynthesis is fighting the battle against this. Photosynthesis. Reactions that are not spontaneous can take energy and make it into a more useful form. So in photosynthesis, we're taking light energy, so we have an investment of energy from outside, which is a form of kinetic energy. And we're turning it into chemical bonds, which is potential energy, which then we will use for kinetic energy. And again, every transformation releases some less useful energy. The energy isn't lost, but it's usually changed into heat. So heat is this less organized energy. So the bear is going to release heat, also carbon dioxide and water, which are less complex molecules. There's a verse in Romans chapter 8:21, and part of the verse says, creation itself will be liberated from its bondage to decay. And that's just me. I was thinking about this when I was reading about the second law of thermodynamics, that creation is bonded to decay and is going downhill. But we have hope, not just in photosynthesis, but in the fact that in Romans 8:22, it tells us that the whole creation has been groaning together as I can't even suffers together the pains of labor, but that it's all of creation is going to be redeemed and redeemed from the bondage of decay, of entropy. So there's our spiritual connection for today that you didn't ask for, but you got anyway. So what does this look like if we're graphing it? Sorry, I didn't mean to circle the 3. I meant to write 8 points. All of these reactions we can classify in terms of their energy, what they look like, products versus reactants. So there's 2 kinds. We can put reactions into 2 categories, exergonic and endergonic.
You might have also heard of these. Sometimes we call them exothermic reactions because sometimes the energy that's released is heat. I contemplated stealing chemistry's fun elephant toothpaste reaction, but I did not. I left that to the chemists. They will show it to you at some point. It's a fun reaction that shows a lot of different things, but I was like, you can also, Mark Rober does world's largest elephant toothpaste. You can Google it. So exergonic just means that the reactants, so these are the reactants in the reaction, and this is the amount of energy that they have more energy than the products of the reaction. So at some point in the progress of the reaction, energy is released. And again, sometimes when it's heat energy, it's an exothermic reaction. So this is just showing us the amount of energy that is released. And we call the form of energy that we're talking about here is delta G, free energy. So delta G is the amount of energy that can actually be used for work. So we're talking about useful energy. Energy that can be used to perform some kind of work. So this reaction has a net release of delta G. And again, an example of this is cellular respiration. So breaking those chemical bonds will release, in this case, adenosine triphosphate, which is cell fuel, which we'll talk more about next chapter. Some people got out early. You're not going to, sorry. The opposite of this is an endergonic reaction. And in this case, our reactants have less energy than the products. So this requires some input of energy into the reaction. So this arrow, the difference between the reactants and the products, shows us the amount of energy that is required for the reaction to happen. So how much energy has to be input? So this energy comes from somewhere. In the surroundings. So if we're talking about photosynthesis, where is that energy coming from? It's coming from the sun. So if we're looking at a reaction and we see that it has a negative delta G reaction, it's a negative delta G. This is a reaction, I don't want to put a dot there, that is going to be spontaneous. So that's going to be an exergonic reaction. In this kind of reaction, we have delta G is going to be positive or 0. This is going to be a reaction that's not spontaneous. It's not going to happen without that input of energy. And there's an equation in your book and that talks about this as delta G being greater than 0 means it will be not spontaneous. Sorry, I should have written that down over there. And this is delta G is less than 0. Remember my singing chemistry professor? She had a song about this. It was written to the tune of Delta Dawn, which is a really, really old song. And she actually wrote to the people and asked for permission to have the copyright rules to write the song with Delta G, the Delta Dawn, and they wouldn't let her, but she taught us it anyway. And that is the only thing I remember, not the only thing, that's one of the only things I remember. And I sang that song in the test and I still didn't remember what it meant, but I could still sing it to you today. Val Delta G, but I won't, because I will spare you that. Okay, quiz today, don't forget to do the quiz. Homework is due Monday, and I did let you out one minute, so. If you didn't sign the attendance sheet, come do it. Why will you not let me out of this? I'm on the struggle bus here trying to end this.
Would you be willing to put this in the,
And Ashley,
yeah,
yes, I'll do that.
thank you.
I'll take it. Thank you. Oh, that's your 7, gotcha.
My 7th, I still have my 8.
Yeah. Wait till Monday, that's safer. When do you leave? Tomorrow, tomorrow morning? Okay, so you get one more night of sleep.
Yeah.
Good luck, have fun. Why are you not letting me out of my PowerPoint? You know how that works.